Okay, everybody, we're ready to go, please. Thank you all for coming. I'm Michael Walker with the Data Science Association, and we are here today for Big Data Business Advantage with GPUs and FPGAs for real-time data processing with Dr. Ron Indek, and I'd like to thank Dr. Indek for traveling here to present for us. It is June 25th, 2014. We're at the University of Colorado, Denver, and just wanted to share with you something that happened to me last week. I took my wife to a James Taylor concert. Now, how many of you like James Taylor? Oh, quite a few. That's wonderful. Yeah, and there was an older audience, there. But at intermission, I'm sitting there with my wife, and this young guy comes up to me. He's about, maybe 19, 20 years old, about the age of my daughter. And he looks at me and he says, "Hey, do you know where I can buy some marijuana?" I look at my wife and she starts laughing, and I look at him and I say, "Do I look like a drug dealer?" I say, "Good luck." I send him on his way. But that was really funny. Anyway, also want to let you know we have two new sponsors, Grid Game, which is a wonderful company, and the Denver Pizza Company. We lost our food sponsor here in Denver, Old Chicago, not because of any bad relationship. We had a wonderful relationship with them, but apparently they weren't getting enough business, so they moved from Market Street. So luckily, we were able to find the Denver Pizza Company. The only problem is they don't have a sit-down place, where we can go afterwards and sit down and have a beer or a cola or something to eat. So we're going to need to find another place. We haven't been able to find another place yet. And if any of you know or can suggest another place nearby within walking distance, perhaps on Market Street, please let me know. Also, want to talk about the Data Science Association. We have a bunch of different committees. And if I'd like to ask people if they're interested to join one of the committees, we really need to develop standards for data science. Nobody's really doing that right now. And we have created a number of different committees to help develop those standards. So for example, we have the Conference Planning Committee, the Standards Committee, the Data Privacy Committee, Education, the Professional Conduct Committee, the Journal, the Certification and Licensure Committee. So I really would like collaboration. We really need your help here. It's not something that just a few of us can do alone. We really need all of your help and your input. So if you're interested, please go to the website, find the committee. You can email the committee chair or just contact us. One thing I wanted to talk about, one thing we're doing is we're going to create this summer an educational curriculum that Michael Malik is chairing. And I am putting together a certification exam so people can get certified in data science. And this is an interesting survey that was done by Birchworks just last month. And it shows here that 46% of data scientists surveyed have PhDs, 42% masters, 11% bachelors, only 1% with no degree. So as you can see, the overwhelming majority of data scientists do have some form of graduate degree. I also want to, yes?
Is there a efficacy chart on which data scientists at which level of degrees are most effective within organizations?
No, but that's really a great idea. I've thought a lot about that, and I think that's something that we should do. I know that in my working with data scientists, I think that astrophysicists have some of the best skills just because they've been trained for a long time in how to deal with large data sets and how to avoid all the large pitfalls. But I think it really depends on the person. I think For me, the best data scientists are people who are really curious, who question the status quo, that often think about what if, that are very skeptical, and think almost like a child. I think too often we all have preconceived notions about how things should work or about how things are working. I think the best data scientists do have certain skill sets and use scientific techniques, but are very creative in how they think. They think differently than most people, and they're able to come up with really creative solutions. But I think we should do a survey on that. That's a great idea. So anyway, I want to let you know we're calling for papers for the International Journal of Data Science. And if you want to get published, you let me know, and I'll make sure that you get published. The deadline's October 1st. I was able to negotiate a different deal with the publisher for professional practitioners because there are really stringent requirements for the academics. And I told the publisher there's no way that the practitioners are going to have enough time to be able to research and comply with all of these requirements. So we have different, more lax requirements. So if you have an idea on something that you're working on or something that you're interested in, let me know, and I'll make sure that you get published. And that's it. Thank you, and let's give a warm welcome to Dr. Ingest.
Well, thank you, Michael, and Michael for inviting me here. Really appreciate the opportunity. Sorry. I'm supposed to be constrained here. I wander when I talk. We have some unusual stuff, some things that we've been working on for the past 2 decades. The academia and industry have been working on doing for the past 4. And so we just wanted to share with you sort of the state of the art, some of the applications that we're working on, some of the successes that we've had, and really, like it says, enabling business advantage. If you can't do that, oftentimes you don't have anything that's viable. And as far as the interaction or dialogue goes, I don't know if you guys need it to be formal for whatever reason, but it can be informal. Okay. So if you have any questions, the light sometimes gets in my eyes, but if you raise your hand or holler, I'll try and stop and then we'll try and address it. Or if you want to ask it at the end, I think there's plenty of time for that. So what nonsense do we have here? You know, I just learned how to spell FPGA, field-programmable gate arrays. Just to kind of level set, does everybody know what an FPGA is? Have you worked with it? You've understood it? Awesome. So we have, for a long time been looking for the kind of compute resources that really give us that advantage, that give us the ability to do the things with the massive amounts of data. And there's always been massive amounts of data. Data has been doubling every 6 months, 12 months, 18 months, depending upon who you are and what you're doing, it's always doubling. It's an exponential growth. And being able to leverage that successfully is really where the rubber meets the road. To store it, I come from the data storage industry, so that's exciting, that's challenging, but that really isn't where we can enable any kind of business advantage. It's being able to use those data effectively. And one of the hypotheses that we started out with is that you're not going to get there. If you're drowning today and the data are doubling, you're not going to get there doing the same thing, just trying to run a little bit faster, get it done a little bit better. We really had to do a paradigm shift. We had to change things up, and that's what we're going to talk about today. So, leveraging business advantage and big data, that's all the rage today. Big data to us a decade ago was unstructured data. One of my colleagues from Informatica, I like how he said that he always asked the audience, do you have data? Everyone says, sure, I have data. Do you got a lot of data? Sure. Do you have problems with it? Yeah, Well, if you're challenged with it, maybe that's one way to think about big data. I know there's a lot of different definitions, and we'll go through some of the things, but really it's being able to leverage the data to your advantage. And what we're doing is leveraging a new kind of system architecture. It really isn't new, but new to the market-ish in the past decade. And it's really, and here's the difference, whether you're a data scientist, an engineer, an architect, a coder, it's really being able to process that data in flight. So as the data is going from wherever it was, Gazeta, doing that stuff and adding value to the data as it's moving. And that's the challenge. But that's the paradigm shift. That's where you can really handle the amount of data, the volume of data, and the challenges that you have with those data. So today, backwards here. So today, we'll just talk a little bit about this advanced processing, some of the challenges that are associated with that, big data, total data, whatever you want to call it. The fact that parallelism is starting to become, or has become, economical, not just in research, not just in big science, but in IT. So that's what's really driving a lot of interesting changes. Then we get into what we wanted to talk about tonight, or featured tonight, this heterogeneous systems architecture. It goes by a lot of different things, but if you take a bunch of different compute resources and stuff them together, that's what heterogeneous systems architecture is all about. And then the implementation and its business impact by being able to, again, address the challenges associated with the vast amounts of data, especially data in flight. If we get time, we'll do a demo, provided that the network stays up. It may or may not interest you, but we'll see whether or not we can drive something there. So this picture has been with me. One of my students went back and found it in the late 90s. I think it may have come up in the early 90s, early to mid 90s. But it's been with me because I just really took a liking to it. And it just says a lot about data and the challenges with the data. So we have this poor fella here who, by all accounts, by all reason, you would think he's a pretty smart guy. He has a beard, so I'm sure he's very learned. And he has a challenge in that he has to address, read through, process, and understand all that data behind it. So in paper format, if you guys want to play with numbers, a sheet of paper on a side can, store a couple of kilobytes of information. A ream of paper, 500 pages, that makes 1,000 sides on the paper, so that goes up to a couple of megabytes per ream. A box of paper is 10 reams, so you get, maybe 30 megabytes. So this guy's challenged with having to process, hundreds of megabytes, gigabytes of data, and doing so in his lifetime. So you might ask, well, how is he going to go through all of that data? How is he going to read it? Now, he's very smart, he can do a lot of different things. He can cut, he can clean, he can read. So he is sort of like that general purpose processor. He's very similar to that CPU in many ways, but most strikingly, I think, in the sense that it's a sequential process that typically the brain will do as you're going through and reading. And all of the von Neumann machines, all the Intels and AMDs and the CPUs of the world are that sequential microprocessor where they can take a byte of data, maybe 2 bytes of data, an instruction every clock cycle. Now, they can do it very quickly. There's, maybe 3 billion instructions that they can go through per second. But that's fundamentally the way they have to do things, the way that this needs to be processed. Line by line, word by word, character by character, you have to go through and process in a sequential fashion. Okay? I would maintain that that's somewhat limiting. Why don't we think about this guy? I'm sure he has a room full of colleagues down the hall. So why don't we recruit them, bring them in, and have them start going through the different documents, the different monographs or tomes that are sitting back there. And each one of them could take, a box of paper and start reading through that. And that helps. That's parallel. They could all then get together at the end of the day or at the end of their year or lifetime and share amongst them as to how they might be able to integrate that data. You could further subdivide the problem, and you could recognize that each one of these guys has, a bunch of graduate students. They're maybe not as smart, but they don't need to be if you give them tasks that are much simpler. And then you could parse all that out to the students in the class or the students in the research lab, and each one of them might have a specific task. Each one of them might be looking for a particular word or a particular phrase or a particular something, and then looks at a page, perhaps, and then passes it on to its colleague who's looking for something else and so on. And while it's passing its book over to the colleague or the page over to the colleague, it can be picking up another page. So really, in every clock cycle, everybody's doing something different, but a lot of work is getting done all at once. So if you start to think about the ways that you can parallelize the problem, so just give it to different processors, really move different data elements, so break the data up into various places and put the compute resources there. And then there's the pipeline parallelism, where you might be able to take a data set, it can be one or many, but you can be doing many different things on it, just like a manufacturing line, just like a car wash, where you can have many different stations as it's going down. And you can have many cars in there, so the throughput and the amount of work getting done can be increased if you think about dividing the problem that way. So from this picture, I think there are a lot of interesting both challenges and solutions that you might bring to bear on this problem. And fundamentally, we're going to do the same thing in the compute world. Remember I said if you're drowning and we can't process the data, and it's just give me your data and I'll process it tomorrow, throw it into a new cluster and I'll process it, in batch in the next hour or 10 or next year or whatever. That's maybe not going to work if you want to be able to access that data quickly with rich content and rich capability. So why this push for understanding competitive advantage as it relates to data? I used to give specific examples, and then in 2012, IBM came out with this CIO survey that it did, and it looked over a 5-year period from 2007 to 2012. I forget how many CIOs that they had interviewed, but they went through and they said, so tell us about your organization, tell us how you leverage data, how you use data, whether it's good or it's bad. And what just blew me away, what was exceptionally striking, is that, of course, we know that analytics can create that competitive advantage, but it's the fact that companies that embrace analytics really accelerate their performance. 20 times the EBITDA and 50% more revenue growth over those 5 years. I mean, wow, if that doesn't encourage you, if not drive you to really using your data effectively, I don't know what would. So the real issue here is the ability to carry that out. And so the CIO who says, yes, I get it, I see that there is a striking advantage to using the data, but how do I do it? I turn to the IT folks, the data scientists, the computer scientists, and sometimes they're left short. So we'll talk about ways in perhaps structuring things so that they can, in fact, address these data and the data challenges. So a couple of things to think about when we think about this total data. Robin Bloor, one of the industry analysts here, used to be a mainframe guy, and then got religion. recognizes that mainframes and the data infrastructure and IT are exceptionally important in the industry, and a lot of effort has gone in, academic, as well as industrial, as well as just a lot of different companies and corporations that have been built around this. And in fact, a lot of those elements, the databases, the data analytics tools, a lot of those things work well. What typically is not really put together yet is that you think about big data or unstructured data and structured data or relational, and it's the and, it isn't one or the other. You want to be able to leverage relational data when you can, when it's appropriate, when it's cost effective, but you also want to be able to leverage the other stuff. And ever since I've been doing this, it seems to be always that 80-20 or 90-10. Yeah, 10% of my data is important, so I structure it, I work with it, so I can analyze it, and the 90% is just out there. Someday I'll get to it. But we're starting to find that a lot of information can be obtained from that stuff that we say is kind of either out of the norm, looking at some of the exceptions. Fraud is a great example. I don't care about all those people who are doing the right thing. We got to find those people who are the outliers, who are doing the things that they're not supposed to do. That's where we find the fraud. That's where we find some of the interesting cases. In medicine, the same thing. Yeah, we definitely want to be able to find out, what's normal, but we also have to understand the outliers. And the only way we can do that is by looking at all of the data. We can't just do a statistical a statistical description of that data and be successful for all of the data. So, I'm getting to that point where it's real dry here. Is there water in here? There you go. Okay. You guys are really dry here. I'm coming from the Midwest where the humidity, I kid you not, the humidity today when I left was 97%.
You're also a mile higher.
A mile higher, yes, yes. Okay, so, really what we want to do is to understand the data, the total data, and as Robin says, it's really the total data flow bottlenecks. Getting the data from one place to another. It isn't just, data flow isn't just a Cisco router moving data from point A to point B. But if you're going to be taking data in from a variety of different sources, you want to at least kind of make them look the same so that when you go and try and access them, the answers will come out much faster. You don't have to do as much work at that point. So if data are moving, then that's the time when you want to be able to process them. So the total data flow bottlenecks. And again, we're back to if you're not processing them in flight, then you have to drop them somewhere, and you have a lot of challenges with that. We'll talk about that. So anyway, of course, data volumes are exploding. This picture, I could have put any year here, because it's always exponential. But this is what IPC says things are growing to be in the amount of exabytes and petabytes and yottabytes, zettabytes, whatever, as the data grow. So we have, in addition to that, Doug from Gartner talks about that velocity and the variety. The fact that data are coming in at different rates. Sometimes they're coming in batch, sometimes they're dribbling in, sometimes it's a fire hose. We have to be able to handle those different processing rates for the data as it's coming in. Different variety, of course, coming from a variety of different sources. Structured, non-structured, yes. But it might be coming from sensor machine data. It might be coming from social media. It might be coming from all sorts of different sources. Are they useful to you? Yeah, when you can start to process it all together, then you can start to do a lot of things, whether it's a security, whether it's enhancing the kind of experience that a customer is going to have, being able to create a competitive advantage, operational excellence, all that stuff. So again, the data tend to be moving between disparate systems, at least the interesting data are moving between disparate systems, and One of the things that's often overlooked is that there is this mainframe stuff, transactional data, great system, but getting the data off that system tends to be challenging because you're already working hard to get it in. So you gotta think about getting it off, and if it's expensive and working hard to get it in, you're gonna spend even more time and money getting it off, so most people don't. Well, again, I think we might have some ideas, some suggestions. I really appreciate it. I knew it was going to be a problem because I was thirsty on the end. Okay. Another thing is, I will not name it. We were at a large health benefits provider just last week, Thursday, I think, and they shared with us a stunning revelation that they are not HIPAA compliant. That is, I mean, you know, who would have thunk? They just can't do it. They just can't, they don't know how to do it. Even though they're compelled to do it, if anyone found out, they would either lose business or certainly get hit with fines and, you know, just, it would be terrible for the industry. But in fact, we've met, you know, card processors that aren't PCI compliant. I mean, because encryption is so hard to do, a lot of people just don't do it. And then data quality is another one of those metrics. So you want to be able to secure the data along the processing. And you also want the data to be of high quality. You're looking for those outliers oftentimes. You can still be looking at you know, major trends and everything else, but if the data are messy or bad or muddy, you know, when we talk about a data lake, Hadoop is a data lake. You know, some of our customers have shared with us, in fact, it's more like a data log because the data go in and they don't know what the quality is. They don't know if it's clean or dirty or what. So, you know, these are kinds of challenges that when you're talking about using the data effectively, you have to address that. So, what are some conventional approaches? We got the old man, the beard, the box, the books, everything. So what we like to do is to add a lot more cores and memory to the existing product. And, you know, conventionally, that is really one of the only toolkits available to general processing folks, unless they do want to take the time to try to build a specific system for a specific data processing capability. But really, you have computational resources, you have memory resources, you have bus bandwidth, and you know that's how you build a modern computational system. And that's where we came in and said, you know, we're going to have to be doing something different because it just doesn't seem like it's going to scale to get us to where we need to be. We appreciated the physics of the system, that it made it tough to get beyond the 3 gigahertz in a clock frequency. Yes, we can add more cores, but if we're drowning today and we're going to double in a year, and then 4 times the next year, and 10 times the next year, that gets to be something. Where are you going to get 10 times the number of cores in 3 years? 10 times the number of memory. You know, that's where this kind of breaks down. We can look at some of the massively parallel processing systems that are out there. So someone has taken the time to glue the compute resources, the memory, the networking infrastructure, everything that's needed to create a good, solid, massively parallel processor. These are just some examples: a Teradata, a Netezza, a Cray, SGI, Exadata from Oracle. You know, being able to process this data in a way, again, makes a lot of sense. But you oftentimes will be pushing processing into this massively parallel system and doing things that it wasn't designed to do. One of the things that this processing, these systems in general were not designed to do was to process data on the fly. So being able to process the data in flight is maybe not the best use for this kind of a system. So we can also look at changing the infrastructure. Oracle Exadata is a system that is an engineered system similar to the massively parallel processors. They would consider it MPP, but it's yet even a different kind of an architecture or structure. So, you know, we'd have to go out and buy it and maintain it and feed it. And so again, we're trying to think about an order of magnitude in 3 years, 2 orders of magnitude 3 years after that. It gets to be quite challenging. Distributed platforms, Hadoop, that's great. Seems like it ought to scale. Everyone knows you just buy systems off of eBay and rock and roll. Well, maybe, maybe not. But again, I challenge you, let's scale a factor of 100 in 6 years and see where we get to. What are the costs? How do we do that processing? Now, it ends up being a terrific place to put data, to process data once they're in batch typically. But again, this isn't going to solve the problem of trying to process the data on ingest or as it's in flight, as it's being generated, created, or moved from its source to its target. So, again, bottom line, it's expensive, it takes time, and the scalability is just something that seems to be beyond where we think we want to be. So we look a little closer at the massively parallel systems. So Amdahl's law, terrific picture here, which really tells you that in fact, so I'm sure none of you can see this, this is the, what they say, speed up, this is the number of processors, and of course it isn't linear, but that's neither here nor there, but the point is, you get a lot of benefit by adding cores, but depending upon the kind of problem, you won't be able to scale ad nauseum. There reaches a point where it starts to saturate for any kind of problem that typically is needed in the industry. So we think about that, and 40 years, almost 50 years, people have, talked about HPC, high performance computing. The history was that systems were expensive. We all know that's why it kind of lived in big science space. Tools were unique and training was required. I think that's an understatement. It was an art. It remains an art today in really getting it. And you talk about performance and tuning, and most people can't even do that. Even if they can get it implemented. Scaling is often self-linear. So today we may have 64 cores in our system, the new processors that are coming out, so 4-socket systems, we can see hundreds of cores coming. But as we start to add cores and threads and bringing the memory down to the process, we see that, double the number of cores, and oftentimes you're only getting maybe 40% improvement in performance. You go 4 times the number of cores, and it tends to get even worse, not better. So, and there are exceptions to the rules, but in general, that's the kind of thing that happens. So for 40 years, it really has struggled to become a really widespread general tool to all industries. And a lot of it, I would maintain, has to do with this ability to be able to, really unique tools and training. Because of the abstraction, there really wasn't any. So you had to sit down and think in parallel. And that's tough. How many of you now maybe if you read, pictographs and other kinds of characters, but how many of you go to the back of a book and look something up like golden retriever and just go to golden retriever? I go to G, and then I go to the GO, and then GOL, and then GOLD, and it's a very sequential process. If we could just put in the search term golden retriever, and it would find that in one clock cycle. That would be pretty cool, I think. But that kind of abstraction is tough. So unless it's abstracted away, you gotta think, you gotta code, you have to implement in parallel. And again, that's often a very difficult, task or challenge for anyone, even in academia or in big science. Very difficult to do. Because we're not. And what we're seeing now is that hardware is becoming a little bit less expensive. I might even say inexpensive. You know, the Hadoop cluster bought on eBay, you know, various parts and pieces that you can just steal and, you know, buy cheap. The application development improvements are getting better, but they're not quite here yet. So if we could think about abstracting all of that implementation and parallelism, and also the streaming process, just abstract it away, and really you just think about gluing together functions and everything underneath is taken care of, that might be a viable way to abstract and actually implement then the high performance computing model. So we'll see where we can get to with that. So instead of just taking straight sequential microprocessors, memory, and networking, and gluing them all together, maybe there's another way that we can skin the cat. So, if we think about leveraging a variety of different compute resources, why? There are some times when we need double precision, high performance computational analytics. There are times when we just need to do bit and byte manipulation. There are times when we need to do different processes on large blocks of data. Sometimes they have to span to different memory regions and data sources and sinks. So different compute resources can be matched or mapped to different processes. If I'm going to be doing some image processing, you know, I might want to bring in something that we know works well. In the 1980s, that CPU, that sequential microprocessor, the guy that does 1 or 2 bytes, you know, one instruction at a time, as the gamers were starting to paint the screen faster and faster with richer colors and more action and more things, the CPU just couldn't cut it. So out comes a graphics processing unit specifically designed for the kind of vector processing that's needed for that kind of painting of the screen very quickly. So if I have problems that I can sort of map into that paradigm, let's grab a GPU. Or if I have processes that require a lot of bit and byte manipulation, like reading golden retriever, you know, as much as that sounds funny, a lot of data today are CSV, for example. So what does a sequential microprocessor have to do? Every byte that comes in, remember, you can work 1 byte or 2, 1 instruction at a time. So the first thing that fellow has to do is, are you a comma? Are you a comma? Are you, oh, you're a comma, okay, so then I can back up, take that, that's 1 bit of data, or, you know, byte, block, whatever. And then, are you a comma? Are you a comma? He has to touch every single byte of data as it's flowing through in order to parse it. Just to parse it. Doesn't even have to do anything. Just parsing the data. So if we can bring the right resources at the right times, then maybe we can gain some incredible advantage. Because if you think about a GPU today, you know, a Tesla coming out from NVIDIA, for example, it might have 2,000 processors on it. Granted that Intel is putting out chips that you know, are 16 and 20 and 24, and we've seen the roadmap, and it goes out even farther. But now we have a chip today that has a couple thousand processors on it. That's terrific. So we're already now leveraging something that's, you know, 3 orders of magnitude better than what you buy or what you use for general purpose processing. Then that other thing, that other alphabet soup, that FPGA, that you guys all know about. You can set that up any way you want. That can have hundreds of thousands of processors on that chip at any instant in time. So for the right kind of problem, you're leveraging orders of magnitude of compute resource for the problem, for the data at the time. So what we'd also like to do is to be able to accommodate that stream processing notions. And the idea there is, once you recognize that leveraging a variety of different compute resources, you can decouple. So here again, for the computer scientists here, you can decouple latency and throughput. For sequential microprocessors, that's impossible. Yeah, I can do more if I take more time on that data. So I have to slow the data down. Now, if you can do more with the data without slowing the data down, you really are starting to get at this concept of stream processing. So you got a source, you got a target, you got some stuff in the middle. Maybe that stuff in the middle is doing HIPAA compliance, securing that data, masking the data where appropriate, which is tough, as we said, and challenging. There are some companies that may not be doing it today. But if we could imagine just dropping in a masking module that does the right stuff at the right time, then I think we might win. Another thing that this does is it can really leverage the different compute resources. It can leverage that fine-grained parallelism. So we can end up with that model of the data parallelism, so you know the different roads that the data can go down, as well as it can leverage the pipeline parallelism of bringing the data in, and in every clock cycle it might be a very deep pipeline doing a lot of stuff on that data as it's flowing through. So, you know, that's that, separating the throughput and latency. And then being able to abstract everything away from the user, so the user doesn't have to think in parallel. The user doesn't have to manage all the different resources. But again, if it could just be sort of this source, target, stuff in the middle, then we might have something that people could use. So again, we've already talked about this, the applications, the CPUs, GPUs, FPGAs, and they do different things. Now with my colleagues, not bad at everything. That's what he teaches the students, that a general purpose processor is just kind of not bad at everything, which is true. But it does some things very good, very well. So let's leverage it there. Thousands of cores, excellent matrix and floating point operations. Whenever we need it, let's recruit that resource. If we don't need it, we don't have to use it. We don't have to force a problem into that compute architecture. FPGAs, again, fully customizable. I could create a GPU or a CPU out of an FPGA. That was what they were first designed to do, was to test those chips. So you didn't have to build them, to spend $10 million building it and then find out you made a mistake. So you can create any engine or any set of engines in that thing. But since you have these two guys already off the shelf, you can put them in, you can use them. We may as well use this for the bit and byte manipulations and the kinds of things that these guys don't do well. And now when you glue it together, now things start to look very interesting. So we can think about this pipeline parallelism, the direct parallelism of having different branches, different things on the branch, and then in every clock cycle, each one of these engines is doing something, or you at least try to arrange the flow so that it's used most efficiently. And in addition to decoupling the latency from throughput, all the good stuff we talked about, oftentimes these systems are going to be terrifically lower power than a conventional system scaled up to do the same kinds of things. And by lower power, it's usually lower power by orders of magnitude. So let me just walk through an example here. Risk management. So we have risk management, whether it's financial technologies or whatever. People need it done. They need it done fast, whether they're looking for internally for their exposure and they're trying to corral that kind of a risk. It might be doing risk for compliance because they're required to have a certain amount of money on hand if they're lending and doing all sorts of borrowing. Whatever, they need to be able to do it quickly, and oftentimes financial. Okay, I've probably given this slide at least 20 times. This fanatical scrutiny here. So one of the things, and if we just use it as an example, stochastic process, you want to be able to wiggle things out, and you want to be able to run a bunch of different simulations. Monte Carlo is one way of doing that, flipping the coin, rolling the dice, whatever, being able to look out, predict, and then shaping the distribution, making some assumptions, and ultimately making some, making some ideas for what you're going to end up doing, so making some decisions. Now, this ends up being an embarrassingly parallel, that actually is a computer architecture term, an embarrassingly parallel application. I can break that problem up into a series of little engines. I can glue them together. We can do direct parallelism and pipeline parallelism, and we can build an engine, a Monte Carlo simulation, a stochastic process that actually is very fast. So what the heck, we did it, we built it. We ended up looking at, in this case, it was a value at risk of our calculation for a basket of stocks, including 4 stocks. What you have to do is you want to be flipping the coin a lot of times in order to get a reasonable sampling of that data. So we execute 1 million trials for each one of those stocks. It's 1 billion coin flips on that data as it goes through. And then there's a variety of different stages in order to meet this value at risk computation from the Monte Carlo. You have a random broad distribution, you shape the distribution, you transpose it, you figure out how much money you may have won or lost, and then you put it into a rank ordering, and then again, as I say, you make the decisions. So that's the mathematical formula. So let's see if we can implement that into a variety of different compute resources. So we ended up looking at the FPGAs, graphics engines, and the processors, and putting stage 1 and stage 2. Those were things, the random flipping of the coin and the processing of that data. That seemed to be fairly good for an FPGA. The CPU is good at pulling apart some of the data, being able to do the transpose, and being able to do that last arithmetic calculation and being able to find out how much money you won or lost. But you can also consider doing this with GPUs. You can have a variety of different stages as it goes through. And typically this last stage, when you have aggregation, you can do that in any of the 3, but in this case, CPU seemed to make some sense. So as we look at that, what we see is by looking at moving that data through, 450,000 walks a second is what a typical, conventional, I think this was Intel, maybe AMD, but microprocessor was able to do those billion walks in 37 minutes with the ancillary computations on it. When we added the FPGA, GPU, and CPU together, and this is all in one box. This isn't a whole plethora of GPUs and a whole room full of FPGAs. It's in one box. You have one FPGA, one GPU, and one CPU. Being able to do this now in only 6 seconds from 37 minutes. So that's 530 times faster. So what took half an hour, you can now do in a couple of seconds, just by appropriately accessing the compute resources. And we know that the FPGA was running probably at 75 watts. The GPU was running up at, I think this one was at about 110 watts, compared with 160 watts of the CPU. And so altogether, not adding that much wattage, but dramatically decreasing the amount of time that it takes to process the data. Okay? When you can start to do things that fast, yes?
What was the performance speed up minus the FPGA, just the GPU and CPU? Do you have a number for that?
Yes, that's in the original paper. I want to say it was about 160. So I think this was really the first academic discussion of GPU, CPUs, and FPGAs. This was in 2006-ish. And I want to say it was about 120, 160, something like that. And so you get a bump. Now, is it worth it for this particular problem to get a factor of 4 or 5? The fact that it's in there, if you think about this as a system, and for this particular problem, I'll take a factor of 4 if it comes relatively for free. Factor of 4, right? So that's like adding 3 more CPUs to your system. But we'll see that in many instances, the FPGA does a lot of the heavy lifting for the kind of data that we see around an enterprise. So that CSV kind of processing, the unstructured text, the data that's coming in from sensors, that kind of stuff is just perfect for the FPGA. Okay, make sense? Yeah.
Your baseline CPU, what level of parallelism were you employing, and how much thread utilization, hybrid threads, how many cores?
Yeah, I knew you were gonna. I knew once somebody asked that, they were gonna go there. And in the paper, I seem to remember it was an 8-core system, and I don't remember how many threads.
Really depends on the software you use to make sure you're using all the cores.
Correct. Yes.
That's the hard part.
That's absolutely correct. And I think that was done pretty well. Because we had the people who developed the CPUs help us with that. So they knew how to run it. Anything else? But again, it's in the original paper. I'm sorry I don't have that data right off the top of my head.
Ron, what's the correlation of watts to the number of simulations? Is there, or is there?
Sure, there is a compute density, there is a compute efficiency, and it's, so that's actually in another paper. I know that's terrible.
Just wondering.
Yeah, so that was a vector that we went down just to talk about the performance, the efficiency of the performance. Okay. So I just wanted to bring up that we're not the only ones doing this. We're not the only ones who have been doing this. This kind of heterogeneous computing architecture has been around in academia for 20 decades, or 20 years, decades or longer. It's just kind of coming to the forefront. Intel announced this week that it was going to be producing a chip, CPU plus FPGA, so a single socket CPU plus FPGA. AMD last year, I gave a talk at their conference last year where they announced their HSA, their Heterogeneous Systems Architecture, which is the CPU plus GPU in one socket. And again, this week, Microsoft announced that Bing is going to be leveraging the FPGA for the searches, because again, it recognizes that the FPGA is massively parallel, doing the kind of text processing and the kind of matching that's necessary for the kind of Bing searches. It's a perfect fit and extremely low power as it's compared to CPUs. Yeah.
Is there any research effort given to the massively parallel algorithms, theoretically, what problems, spaces map to what architecture?
Yeah, so that used to live in computer science, and I think now as the data scientists are, coming into a a discipline of their own, if you will, and do some of the things that you're talking about. There is academic research. We've done some. There are plenty of universities out there that are doing it and saying, yes, in fact, these kinds of problems tend to map to this kind of an architecture. And again, that's fairly well known for those in that industry, in that academic side. But where I think things get challenging is being able to deploy that in the real world for a variety of different applications. So again, if you can narrow your focus and all you're doing is Monte Carlo simulations for risk analytics, sure, we can build a system that does just that. But what if you also want to be doing genomics applications on it? What if you also want to be doing searches on it? Does it make sense to build kind of a general purpose heterogeneous compute appliance? I think it does. I think that the time has come, and Intel, AMD, and Microsoft, and several others, SGI. So several years ago, we were working with SGI on a project that they called RASC, Reconfigurable Application Specific Computing. It never really made it. And a lot of the things that we were doing were basically the engines back behind it. So it's been around there, but I think now it is squarely here today. And I think there's a variety of different applications now that can be applied to this. Again, whether it's security, analytics, or biocomputation. Okay. All right, so I tried to sell you on the fact that this heterogeneous systems architecture is a fruitful approach. And I think that what's been missing is instead of building just a general purpose platform, which people have done, they've tried, 40 companies at least have done it, including SGI with reconfigurable application-specific computing, being able to abstract it away so that you don't have to code to the FPGAs in VHDL or Verilog, so that you don't have to really get engaged with CUDA or whatever your parallel GPU processing design environment is. You don't have to think about the multi-threads. If that were all abstracted away, and again, you could just drag and drop kind of the functionality, and the system configured itself to become the engine that it needed to be, then I think we have a good winning recipe. So again, this particular abstraction, I think, gives us this stream processing. Yeah.
You see promising research out there in languages beyond the usual suspects today, where the parallelization is more implicit rather than explicit?
Yes. Yes. So that's a different talk that I want to stay away from. What I would say is that's what somebody is going to use to create that kind of an appliance, but let's focus on the appliance and we'll abstract it away. Like maybe after we talk about that.
Your second question, do you believe you wind up needing to go with some kind of new architecture for memory in order to feed these CPUs faster?
Sure. Yeah.
Flash? Anybody out there building anything that you see promising?
Yes, and it depends upon how you are going to be accessing that data. Flash. So it depends upon how fast the data can be changing. So, do you want to go to DRAM? Do you want to go to Flash? You could think about other kinds of extended data storage, even magnetic. Everyone hates magnetic, but it's cheap and it works well for what it was designed to do. So if you need to be sequentially streaming data off, it's a great place to put your data and take it off. So being able to understand and appreciate the different levels of cache and the different layers of access and accessibility to that data, then I think you're going to win. So to your real question, do we see things that are coming out? All the major chip manufacturers and storage vendors are working on some things that I think are quite promising. And we're going to see changes in systems architecture tomorrow, for sure. Okay? Okay, so this is one example of an appliance that has been focused on the kind of data processing that one might do as it's coming from the ingest side, the sources again, whether it's machine data, whether it's log data, whether it's transactional data coming off the mainframe or whatever. This same system, by the way, also does blast computations and other bio computations, 10,000 times faster than other processes. So it's the same architecture, just different application running on top of it. But what we see here are a variety of different things that people want to do to the data. And if we look at the conventional kind of rates that people are typically working with, people work with hundreds to thousands, maybe tens of thousands of data records or throughput of the data as it's moving through, given this kind of functionality. On the same, this is not a rack of equipment or a room full of equipment. This is a GPU, FPGA, and CPU system all sitting together in a 7-inch high system. We see that we can get data coming up at hundreds of thousands to millions of records per second. So again, hundreds to thousands of improvement in performance on the data as it's going through. And because it's a stream processor, what you'll see if we have a little bit of time, as you add functions, are we going to slow the data down? If you do 1 or 10 things, how fast is the data going to move through? You know the answer. We decouple the throughput and latency so we can process 10 things just as fast as we can process 1. So, think about it as a true stream processor. That if one system is going to send a million messages through, and it's doing processing, for example, it's masking data, and then you want to do geo-processing or address processing or sorting on the data, look up and replace, which is a join. If you want to be doing that, streaming, it's not going to slow the data down. So, different concept, right? Yeah.
Now, all of these operations that you have here, these capabilities that you have listed, are iterative, highly paralleled algorithms. Basically, translation, iterative type things that are work very, very well in the GPU matrix operations. How do you handle, and you show some pretty impressive performance improvements, but how do you handle things with different conditions, let's say decision trees and decision forests? How does the platform hold up in those particular cases? So
you would use a different compute resource. Maybe the GPU isn't the best, but something like the FPGA would be better for that. Some of the, you talk about the ability for the GPU to handle some of the parallelism, but actually some of the recursive things aren't as good on the GPU as on the FPGA because we can unroll it. Remember, an FPGA can be any engine that we want at any instant in time. So if what we need to do is unroll it, and then we have this great pipeline parallelism as the data are moving through, then that's a good. So if we have decision trees, decision points, we can have the data flow through a specific engine that actually implements that kind of a decision set.
So you offloaded the branch logic onto
Yes.
the FPGA.
Correct. And sometimes where's the different picture? The CPU sometimes can be very good at that branching logic. So again, it depends upon what that workflow looks like, what the data is going to do as it's moving through. Okay. Okay. This is a specific example. I'll just go real quickly to this cartoon. This gives you a sense for what it is we're trying to do. When I talk about stream processing, how it fits into an architecture, whether an enterprise architecture or just about anything else. So these arrows, they are bidirectional. You can think about data coming off the mainframe into a stream processing system, and if it's fast enough, really, by the time the data moves off and back, you really haven't lost much, much time at all. But yet, you can do extremely, extensively rich processing on that data as it's flowing through the system. The data can go from one source or sink to another, or it can be multiple sources that are all going into a particular sink, or vice versa. Oftentimes people nowadays are saying, we got all this great data that's locked up in the mainframe, so maybe we want to turn that into something that we can use for the operational advantage or for the business excellence, being able to drop the data down into there. But you want to be able to drop the data in a form where it's ready to consume. You don't want to, every time you hit that data, you have to think about what you have to do and match to process it, to clean it up, to organize it, to structure it and all that. A priori, you probably know 90% of what you want to do with that data before it lands. So you may as well do it in flight. So not just moving data bits and bytes from one place to another through our router, but let's move it through something that's massively parallel that can do a variety of different things. Have I run out of time?
So there's an arrow up there. I'm wondering if you also support Kafka as a data source.
So yes. So being able to ingest, from a variety of different sources into Hadoop, that's something that is fully supportable.
So not necessarily with Hadoop, you just have, a click stream coming in through a server farm, and all those clicks are coming through and getting migrated into a single Kafka server farm. Can you plug in an Ethernet cable from Kafka's server farm and ingest that way?
Yes. The only limitation is if the network has the bandwidth. So we typically are working with a 10 gig or InfiniBand. So 20 gigabit or 40 gigabit tends to be the size of the pipe that anyone has. Fundamentally, the system can go faster, but if from that Kafka server farm, if you can plug in a couple of 10 gig lines and address all of that data flow, then that can be ingested into here, processed fully, and then dropped wherever you want it to go. Typically, the questions that, the processes that are recruited onto this system are beyond that. So it isn't just moving the data through and doing some sort of either low-level aggregation, but really starting to do the pre-analytics on that data because it is able to aggregate. It's one connection point into that data set. And so that's a good place for you to do the pre-analytics stages. Okay? Yeah.
Backplane issues. I noticed you had some NVIDIA devices, and my understanding is they tend to be plugged in PCI or
PCIe, Gen 3.
Where you hit the saturation points on PCIe here?
It's anywhere from 2.5 to 5 gigabytes a second.
Do you have multiple backlights and mounts, or?
Yes.
Yeah.
Yes.
I mean NetDMA. Certainly DMA on the backplane, but the NetDMA stuff that's coming out.
So in another application, yes, we have not needed that here.
That's the point.
Okay. Yeah.
So programming that data massaging in some sort of optimal way sounds to me like a huge research project, like a Monte Carlo example.
Right,
So, is it a research project?
not anymore. There it is. So this is graphically, and again, I apologize, but we'll finish up here quick. So this is a workflow. So think about it. This is a mainframe to Hadoop workflow. So this, if we go back to that one cartoon, this is data coming out, going in there. Typically what people are doing today is they either drop it down into here and then they think about what they want to do after it's there, or they do a lot of the processing here where it's very expensive and can be slow. This is just think about connecting that transactional data as it comes in over to Hadoop and doing that processing. Well, what kind of processing? So here we're taking mainframe, comes in Epsidic, we gotta do Epsidic nasty, it's COBOL copybooks are just terrible. COBOL, I don't even know how to spell COBOL. I just figured out how to spell FPGA. So, I mean, it's just terrible to deal with that, but with tools that are embedded, you press a button and it does that parsing for you. Then you can drag and drop the appropriate functionality that you want. Validation, making sure that the fields are what they say they are. Key generation, 1, 2, 3 fields, generating keys or whatever. Formatting the data or reformatting the data. Doing a lookup and replace. Address standardization, masking of the data, transforming of the data, whatever. It's just drag and drop. And then on the output, this goes CSV out to Hadoop.
Is this via some kind of API, or is it?
It could be an API. So actually it was built, and there's another whole organization we have that is running the engines on Wall Street. The large banks, hedge funds, exchanges are running these exact same devices. They're just painted red instead of blue. And they're doing a lot of the coding to it or programming of it, but we don't really even think about it as coding or programming. It's accessing those functions through an API. In this world, we've been surprised, but pleasantly so, I guess. People like to access it just through a GUI, drag and drop. I know what I want, so I'm just going to drag and drop it, configure it up to that, and that's it.
Does that work on completely unstructured data at the front end?
It can. It can. Most people don't have completely unstructured data. They may have unstructured fields. They may have, sensor data that may have, some bit of unstructuredness to it. But oftentimes there's enough structure that you can do something. You might argue that words themselves are structured because they have spaces in between. So, but yes, it can. The first application of this actually, after biocomputation 12 years ago, was in government intelligence. And so some of those things that you read about the intelligence community may in fact be true. Yes?
I'm assuming what you have there is what's going on in your velocity box from your previous slide.
Yes.
Right. So that was very familiar with the ETL dynamic.
Yep.
So you had an ETL box on the other slide. So what would the ETL box serve?
So if I went back up to that palette, we might not have everything in that palette. So there might be some things around data governance, some other things around business logic maybe that are retained in that ETL appliance. So there are certain things an ETL appliance does and does well. So again,
you provide all the functionality like that.
Indeed, it is not the entire functionality. So just wait, but not yet. Alrighty, almost there, guys. So this is a little bit different, but I think it gets to the things that we've been talking about in a different way. In the sense that, again, taking a variety of different data, huge volumes, as we know, whether it's the sensor data, distributed power grid, web logs, and blah, 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 tons and tons of stuff. Bringing that in and trying to integrate, synthesize that data so that you can create new information from that data. Again, what the intelligence community may have been, like to do, to be able to pull things together and to make decisions based on that, critical decisions, so that oftentimes you'll think about doing decisions in real time. You'll have a real-time need, maybe it's that risk analytics that we talked about. Sometimes you would want to take that data or some of the data and drop it down to a data warehouse or other data analytics appliance. Other times you may want to drop it down to your data lake or other kinds of things that a Hadoop cluster can do for you. And maybe you think about this as all of the data going all three places, that's perfectly fine, as long as you can handle that data here. Oftentimes the data here will go out and get dropped on the floor. Here they'll be used for deeper analytics, and here, we're still trying to figure out where best to use those data. So we've been talking with a couple of customers about being able to leverage both real-time analytics and conventional batch, because sometimes the data that you see in real time can inform some of the deeper historical analytics that you can do over here, and vice versa. If you have some data that you can look back and add to the real-time data as it's streaming through, you really can inform that data to give you the best. In this case, I wrote operational analytics to give you the best of that capability from that data that exists throughout an enterprise. So again, I think we think about this as not stream processing or Hadoop. Hadoop does great stuff, and I know this is a Hadoop-focused group, but stream processing and Hadoop. Having an Hadoop cluster is awesome, being able to provide that with real-time data, making sure that those data are cleansed, are of a value that really give that final resting place or a temporary resting place a lot more punch, then it makes sense to sit a single appliance out front. These appliances, so if you run the numbers, these appliances are running at tens of terabytes per day flat out without saturating. So a lot of throughput through that particular kind of approach. So the kinds of things we had someone pharmaceutical query. They were trying to look at a variety of different 200,000 search terms and 50 million different medical records, and it changed all the time. And they were running literally. They would come in on Monday. They would fire off a query, go off for the week, and then come back the next Monday and see what the results were, tweak it, run off, and do the things that people at pharmaceutical places do. We took this system, set it in the researcher's office, literally on his desk, ran the same query from 8 days down to 20 minutes, 18 minutes. So that was dramatically different for him. The way that he approaches problems now are so different because he can go down many more paths, and he can go deeper into each one of those paths, asking questions in a single day. Not in a week, but just in a single day. So being able to process, I was sharing with you today, just ran a pilot on somebody who was running, they were struggling with getting 200 records per second through their system. And they thought that was great. They were meeting their SLAs just barely. And we came in and just dropped in the system and showed that they could do that with 50,000 records a second. So hundreds of times, thousands of times faster than what they're doing today. Being able to improve the process, and these are some large scale operations that they're doing every day. Being able to improve by fivefold the task that they were doing, but more importantly, they had to cut it up into 7 different segments to make sure that they could process it, recover from a failure, and so on. We glued everything back together, so reduced complexity, and was able to get this kind of performance. Being able to process the data for analytics, so the data are coming into the mainframe and then out to Hadoop at line rates. As fast as the data comes in, it goes through all that you know, COBOL nonsense and EBCDIC to ASCII and COP3 and all that stuff comes out ASCII or x86 ready. Being able to process and you know, be able to bring that data into the market and be able to create a sellable event. This is that, you know, target knowing that somebody is pregnant. But in fact, you know, that is real analytics. People wanting to, so we're working with a couple of companies, but you know, one of the ones on aisle 411 who's following you around as you're going through the stores, and then being able to say, oh, you know, you bought ketchup 3 weeks ago, you probably need some more. Ketchup is right around the corner. I know that sounds weird and maybe intrusive, but a lot of people appreciate that. So being able to process that data in real time and get it to where it needs to be, again, is something that I think a lot of people just haven't seen before. Customer support, again, you know, taking data and being able to get it in seconds to where it needs to be. They have been living, the CSR had been living in the world of, I can't answer that question today, call back tomorrow. Not a good place for happy customers. So, you know, being able to bring data in and sort it on multi-field keys, and being able to process at millions per second is, again, something, you know, think about that, it's almost a contradiction in terms, a stream sorting engine. Now, to be clear and fair, in fact, you must bring all the data in, but by the time the instant that we see the last record come in, out come sorted records, okay, at these rates, being able to feed it at you know, millions per second. And then being able to, you know, process address, USPS addresses and so on. So, what I had planned to do, but I know it's gotten awfully late, so maybe we can do it offline.
Another 20.
Oh, really? Are you kidding me? Oh, awesome.
We normally have 2 speakers, we gave you 2 slots.
All right. So.
And also,
Yes.
if after the live demo, you might be able to show us some source code that invokes velocity data, whether that be C++ calling APIs or a GUI, drag and drop.
Yeah, and so what we'll do, you know, I can show you what it looks like. It's running on this thing. So this is what's back behind the GUI, but we'll talk about that in a second. So what I thought I'd do, these numbers, not only is this whole concept of being able to process data in flight might be a little bit new, but these numbers are striking, which I guess.
Yeah, I have a question about
Sure.
those numbers that you put out. You had millions and millions of records per second being processed. GPUs have never been infamous, or they've been infamous about data integrity issues. As you're pushing all of these millions and millions of records through and billions of bytes per second,
Do we lose a bit?
yeah, do you lose a bit, and how do you mitigate that?
So how we mitigate it is we make sure that the systems that we put together have the appropriate ECC built in. So we're not using, for our applications, we're not using the $300, $500 GPU. This will be the more expensive, you know, K20, K40 that has ECC built in, the $4,000 cards and whatever, retail $4,000 cards. And that's actually a very important point. FPGA world is the same way. You know, you have to stress these data. So we went through, we qualify our vendors by sending at a minimum a petabyte of data through. And it has to be error-free, otherwise it just doesn't work. And we had a vendor who was in the military side, interestingly enough, but they were on the imaging side. So they weren't GPUs, they were FPGAs, but they were dealing with images. And you know, what's a sparkly here and there? So we were getting through a gigabyte of data and finding 1 bit, but that's a gigabyte of data, what do you want? And I said, okay, so that is your bank account, and we just zeroed out your bank account. Or that was your medical record, and now you have, you know, appendicitis instead of a heart condition. And needless to say, literally after that discussion, we just pulled out of the running and they said, we just don't qualify. So all of our systems do in fact have the level of ECC that ensures that we can put, you know, petabytes of data through without any errors. Is it always going to be that way? Can a gamma ray come in and send off 2 bits or 3 bits and get something? It's possible, yes.
So you don't handle multi-bit errors right now?
Pardon me?
You don't handle multi-bit error.
We can handle 2, I believe, but not meant more than that. Yes, that's right. So, but we have done, you know, the tests on the data quality and just haven't seen any issues. So, okay. All right. So these numbers that we talk about, the throughput, you know, being able to put millions of records through a second, or being able to, you know, handle terabytes, tens of terabytes of data a day in a little appliance like this, just seems unconscionable. I mean, it's just impossible to be able to do that. So what we're doing, if we're actually live here, we have 3 systems in St. Louis, where all the humidity is, where we're taking data and streaming data off of just a source system. In this case, did I pull up the mainframe? Yeah. In this case, it's mainframe data, so EBCDIC is coming out, going into our system, doing the transformation. That's the first step it has to do. Then it goes through some formatting, surrogate key generation, USPS address processing, lookups and replaces, and then out as a flat file off to a third system, which is acting as catch-up. So that would be, if you will, our Hadoop cluster or Teradata system or whatever. So we're going to run through, and these are data. When it sits here, oftentimes the VPN will shut us out after an hour, and it's been up for more than an hour, so we're good. So what we did is we took 1.1 million records that were based on, they've been obfuscated, but they were based on customer data that came in. I think this particular data set is 65 fields wide. It moves through, and these processes then go through and finish in 7.2 seconds. So we're running a couple 100,000, 150,000 records a second through on this particular system with this particular data. It's some pretty massive data. So, because I think each data record can be up to 3K in size. Now we say, wait a minute, guys. I have some precious data in here. So I want to be able to mask those elements, and we'll look at what it is back behind the curtain. I think it's 4 different names, social security number, I don't know what else they have in there. But we're now going to run format preserving masking. So for those of you that know about this, I'll just remind the rest that format preserving masking is 10 rounds of AES encryption with 128-bit division in between. So the problem isn't so much the 10 rounds of AES, but does anyone know of the 128-bit processor? We got 32-bit, 64-bit, but we're going to have 128-bit processors. So that becomes a huge challenge. And people tend to move data through at, 10 to 100 records per second. But because you can create a 128-bit divisor in an FPGA, no problem. So we now have built a format preserving masking engine that now can run at flying rates. But that's the end of the story. So we'll take this data, same data now, coming off the system, moving through, going out to our target. And while most people would have said that that first process would take, hours to complete, if it completed at all, in order to and format preserving masking, I mean, it's just a non-starter. We just aren't going to go there because it'll never finish. So you guys already know the answer, that we're going to process the 1.1 million records in how much time? 7.3 seconds. But I mean, you know, we can run it again, it'll come out 7.2. But the point is, that engine that was in there, or that's in there now, is an extra engine. It isn't the same CPU that is now tasked with doing yet another operation. We're bringing to that flow a new engine of format preserving masking. Okay? And that's why we can set up all of these processes. We can drag and drop other things from the bottom, from that, from this palette. So it isn't a full palette. It is the bottlenecks that the industry has said are challenging in a conventional ETL appliance. So someone had asked about an ETL appliance and what's left. So there are plenty of things that an ETL appliance can do well. We could too, and we will, but for right now, this is what people have needed to be able to process their data. And while you ask your question, let me just show you then what's back behind the curtain.
I saw a database palette down at the bottom. One of the gentlemen here asking questions about the for us and that sort of thing. The hardest part of that in real time is bringing the historic data forward to join with real-time data and doing that in a manner that is timely enough to permit the execution of scoring engine. What is your technology for the database engine, and are you limited to a database that fits in the RAM?
So no to the last, but we do cache. So typically, if we're looking at historical data, people have already prescribed what data they want to be comparing against. So they have a set of master data records, 100 records that they want, could be terabytes big or whatever, but they will stage those then into the system and allow them the data sort of in memory, but really in cache or on demand without stressing the operational data warehouse. You can take changes as the data come in, but the strategy really is to offload it, including that lookup, so you manage the data in cache.
I'm confused by the answer, perhaps I'm missing something. So,
Okay.
In order to conduct that join at something near real-time speed, are you relying on a replicate database in its entirety, complete with spinning storage inside the appliance, or are you caching the data all in? That's why I asked my question about doing that. That's the place that HPC guys want to go. You say big data, and the new HPC guy gets this all here. There's ways to fix that other ways. That's what I'm asking about. Because that is a very limiting problem when you start applying this in big data.
Right.
Some kind of super scoring engine.
So if you need to be accessing the entire data set, then yes, we would have to move everything over. But we have not found a problem yet where somebody has said, you need to be doing the entire data set. They always have a subsetting to data. It may be big, it may be terabytes big, but it's never hundreds of terabytes, petabytes big. If it is, that would be limiting, that would be Yeah.
But there was another data nuggets that was the size of people's analytical data sets, and the peak of the curve is surprisingly small, well within the confines of a nice fat 4U server with a half a terabyte RAM. So we're seeing RAM almost grow faster than servers than people's imagination around bringing enough data together or using enough features out of their data set to run. So I can take something more that sort of thing. So, this may be the line as it grows, the capability of the analytics stack grows.
Yes.
The Teradata guys are playing with FPGAs.
Sure, and Netezza has FPGAs in it already.
Yeah,
so.
that's a parser.
Correct. That's right. It's on the query side. That's
slick tool, but for its easy.
Good. Yes.
So for each of these icons on the bottom, are there CPU, GPU, and FPGA implementations behind them, and some schedule figures out what the optimal flow is?
Yes. Correct. So it can be. So we develop everything, if it can be done, that makes sense. We have instantiations of engines on all three resources. So then the system, can be configured to, depending upon the rest of the workflow and the rest of the elements, it'll be configured to, run through quickly and efficiently. But again, the user doesn't. The user has. Sorry. So this is, what so what are we doing here? We're looking at, the social security number, first, last, and middle name, I guess, is what we're encrypting here. But really, the user just wants to drag and drop this stuff, doesn't want to worry about threads or memory or anything. We take care of all of the stuff with pinning processes to different cores, down to the level of somebody else. Maybe you were talking about, core 0 is not the same as core 1, is not the same as core 2. We actually know which ones do things a little bit better because of the way that it was actually fabricated and mapped to memory.
So do you guys pay any patent royalties to National Instruments?
No, why to National Instruments? Because of the drag and drop, the GUI? Yeah. I think everybody has a GUI. This actually is a GUI that was patterned after Talon, because we looked at Informatica and people said, we would like to see a Talon-ish. So this is what this is kind of patterned after. Yeah.
One of the biggest challenges I have with these massive Excel-type processes is the manageability of the code, maintainability of it. Is what you have here, is it somehow callable from a higher level language?
Yes.
What is that like from an application maintenance standpoint?
So, how do I answer that? So let's say you do have a particular stage in data stage or a particular engine, process in Informatica that you want to call out through our API. And if you change the process in Informatica, it will push out to us, and we would accommodate that. So I know that's not very good. Give me a different way of asking that question. Ask it a different. So maintainability.
So I find is that if I have 40 different feeds coming into a big analytical environment, I may only have one where I have true performance challenges. The other 40 or so, my challenges are the complexity of the data transformation and maintaining the code. What I'm wondering is, could I add this to my processing so I can use this to speed up that one feed that's really challenging to scale up to? And then if I did so, now I have two different technologies. How much complexity can I put in here before this becomes hard to manage from a business rules perspective?
I don't have a good answer for that. I understand the question. I'm trying to think of examples. We have not yet come up against issues that are difficult to manage. And for your application, while it's a great place for us to play, to be that ingest for a troubling set of feeds. Being able to manage it has not been an issue because I think it's been easy. It's very abstracted, so the manageability of it, as you see that behind these widgets, is just XML. So it's very easy to work within that code and code base. People understand it and work with it. But again, we haven't hit that boundary yet where people have said this is too tough. And as far as it being a different tool, yeah, it does have nuances that look and feel differently, and we're working with different companies to try to make it more integrated so you wouldn't even think about it. But we tend to give up so much on performance that we are at this point today. So and Ben, I don't have a good answer. Good question, terrible answer. Yeah, good.
One of the things that Talon does is they've got an ecosystem of people who built their own. What you're providing maybe an SDK for people to prototype, say, machine learning algorithms, and then possibly an Amazon style where I want to start something up, explore it, and then submit my widget on the bottom into like an ecosystem that somebody else might incorporate into their system.
So yes, we're actually talking with a couple of different companies, including Talon, about such things. Yes, it isn't here today, but yes, actually, let's talk it.
What's the price point for these for velocity data for one of the service in comparison to, let's say, a 24-core Xeon system?
So a 24-core Xeon system is probably going to run you on 15K all decked out.
About 22, 28, yeah.
Okay. That seems odd, but the way that our system is priced is a subscription model. So it's independent of data. So it's just per month you get charged, X amount, and that's it. And it includes all of the systems that are needed within the organization for development, testing, QA, disaster recovery, and so on.
So you roll the box in?
Yes, boxes typically. Redundant pair for production, and then disaster recovery and dev testing. But it has that the model where people then start to use it. They find a use case that kind of pays for itself, and then they go, oh, so that finished in 20 seconds. I want to load that box up, so they keep moving more and more use cases to it, and they're free. So, yeah.
Using Informatica as an example, Informatica has an engine, and then all of its code is stored in the repository database that's just separate, and we have two separate services. How does Velocity manage its metadata, its code? Is it all within the same engine itself, or how is that handled?
Today it is, yes.
It isn't a separate repository?
No, it's all managed together. So when we need to do, for data governance, we typically will rely on the existing infrastructure. So we stay out of it and let, for example, Informatica handle the metadata management. Yeah.
Two questions.
Uh-huh.
So within a single box, how many elements do you have? Like how many FPGA words?
So at one level, I would say you don't care, but technically we can have up to 2 FPGAs, 2 GPUs, and it's a 4-socket system with a ton of memory and disk and SSD.
So as you're driving and dropping your functional model, so for FPGAs, you may reprogram them by everything. But from a footprint, in terms of how much FPGA space retail sort of takes up, what's the maximum number of functions that you can pack, assuming pipeline?
And again, that's something, so if you're asking technically, yes, there is a limit, because there's, a maximum size of the Xilinx or Altera FPGA. And maybe there are 2 FPGAs on one board, we could have 2 boards in there. And it depends upon, so let's say that the key generation and the encryption are deposited in there, that will take up a certain amount. If the workflow is different, it would take up a different amount. But, being able to manage it and schedule that and work that through, that's done under the covers. So
the reason I ask is because it's been a decision, I understand. When you have different stages, that are pipeline or whatever, if you have to cross the boundary between one card and the next, right, then that interconnects and become the bottom line. So that's PCI for
right.
So so there's an optimization in terms of what order you need to do things.
Correct.
It's not always linear. So that's what I was wondering. So from an end user perspective, if I'm just driving a car, I may not have an appreciation for what I really asked. So for example, you have a regex element that, depending on number of rules, it's going to take a different amount of.
Correct. That's right.
So, so optimizing that flow and deciding to branch and do parallel flow, given you have to go across multiple elements, and your primary element that is the PCIe interface. How do you make those decisions?
So really, it's more about flow. Remember, we're a streaming engine. So what we try to do is we recognize it definitely will be going through the PCIe bus and out, through, it comes in, it goes out, and through the PCIe bus. What you don't want is it ping-ponging back and forth. So you ensure that instantiates into a workflow that crosses the bus the least amount that it can. Okay, so you don't want it going back and forth from a GPU to an FPGA or from two FPGA cards or whatever. There was another one. Okay.
For one of your smaller systems, what can I look at as cost of entry?
For,
let's say, one of your minimal systems, I only need to process maybe, I don't know, maybe 1 million records a day. So we're probably looking at 1 or 2 boxes, or 3 or 4 boxes, depending on your configuration. So what could I be looking at as a cost of acquisition and first year maintenance and training?
so again, it's a subscription model, so there is no cost of acquisition. So it's just a monthly fee. And list price for something like what you're describing is anywhere between 50, 75K, something like that.
Per month.
Per month.
Yeah, per month. And is there training available?
Oh, sure. That comes in the package.
Sure. Great, thank you.
Yeah. It's recognizing that it's a little bit different. We just make sure everybody gets in, gets happy, gets into production doing what they need to do. And training also isn't heavy. Remember, you're not learning a new language. Training is 2 days. 1 day is typically for the IT folks and networking, managing, understanding the interface, understanding errors and all that stuff. The other day is for more of the straight up developer that understands how to work the flows and talk to the ins and outs. That's it.
Well, I have developers and stuff that really like to add their own features into the product, their own functionality, their own algorithms. What kind of vehicle do I have today to be able to engage and enable them?
Right, so today, typically, if it's a very sophisticated algorithm, we don't have a good way for you to implement it. If it doesn't fit into these standard capabilities, the standard palette, then we don't do it. Yes, we can do biocomputation, but you don't see that on your palette because that's a different, functionality. You don't see the Monte Carlo on there. Yeah, we can do it, but it's not on there. But if you had something completely different, we would either work with you to try to figure out, remember, we're not a general purpose platform, we're an appliance, and just have different market verticals. And this is enterprise data, streaming data for big data.
Data conditioning.
Data conditioning, yes, exactly right. That's right. Yeah.
Do you offer the ability to take one of the script programming languages, compile it into at least one of the dense hardware stuff that you offer, say C++ to one of the modules?
Fundamentally, yes. Sort of leveraging what I just said there, that is not exposed to the customer today. For Nothing other than it's, we want to make sure we can maintain what we have.
And if
You can do some bad things, and if unchecked, yes.
Have you given any thought to, so one of the things we're seeing in our business, I'm in the element space, the emergence of the great interest, 80% of our pipeline. And we're seeing a couple of battles underway, and one of those battles is to do everything in as good as it is and suffer the penalties you can produce along with it. And they're not 10x, just in case anybody's wondering, it's 10x and penalties. And we're seeing some alternate architectures where you're essentially building systems like this on the same nodes as Hadoop, but in it alongside ours as a pure Linux task. We thought about doing that sort of thing. I know some people have talked about utilizing FPGAs in the back way they do for certain specialized stuff. What you're thinking?
It's not here yet. I think it's doable, and we've been talking with a variety of different, both organizations, Open FPGA, others, and some of the service providers. Okay. You know, you can rent, at AWS, you can rent GPUs, and, you know, perhaps someday you'll be able to rent FPGAs. But again, do we want to rent them at the HDL Verilog code stage, or do we want to rent them at the applications or?
There's the rub.
What's that?
There's the rub.
Yeah.
Yeah. There are a lot of programs with your product.
Yep. And if you know any more, we can always use them.
Yeah, let's use that.
Yeah. Anything else? God, I finally put everyone to sleep. Okay. All righty. So, you know, if you have any questions, I'm more than happy to either take them offline, if you haven't wanted to ask them here, or my coordinates. So, all right, so R-index, R-index, R-I-N-D-E-C-K, no dot slashes or spaces, R-index at Velocidata, VELOCIDATA.com. So, or come up and I can give you a card. But thank you. This was awesome. Great group.
Yeah, thank you so much, Doctor. Thank you. Thank you all for coming. We'll see you next month. I think we're at Galvanize in Denver. So thank you. That's basically what I was. Oh, okay, wonderful. Yeah.
We look forward to seeing you.
No, I would have insisted.